Hello, welcome to a video lesson here for Measurement Relationships Unit. This is lesson 7. We're talking about optimizing square-based pyramids. At this point, we have talked about optimization as a process, and we know that we can use it to maximize or minimize some sort of measurement if we're given some specific fixed amount. So in this one, what we're going to do is we're going to minimize the surface area while also maximizing volume of a square-based prism. So this is a very specific shape. A square-based prism is pretty much just like a box. So let's get started here. So Reese Puffs, quite possibly the best cereal of all time. Just a little side note there. But just to get back on track, we're talking about minimizing surface area and maximizing volume. So you got to think to yourself, when is it convenient to minimize surface area? In the last lesson, we talked about maximizing area, getting the most possible space. Well, minimizing surface area makes sense if you're working with materials. So you want to think like you want to use as little materials as possible. And the reason for that is because materials cost money. So you want to use the least amount so that you can save money for your company or whatever it is that you're working for, or if you're building something, it's coming out of your pocket. So you want to save money. The goal is to get the most volume with the least surface area. Okay, so you can use the least amount of space, save money, and still get a lot of volume. So if you're going to minimize surface area of a rectangular prism, just imagine for a second that you have this rectangular prism. Which I'm just going to assume that you kind of know, roughly what they look like. I'll just quickly kind of sketch one here for you. It's pretty much the cereal box or the milk carton. So that's kind of like a rectangular prism. If we know that we want to have a fixed volume of 16 centimeters cubed, the question is what dimensions will minimize the surface area? So what will make this thing have the least surface area but still have a volume of 16 centimeters cubed? Now the answer to this question lies in our last lesson. When we talked about rectangles in general, remember we took a rectangular field and we kind of adjusted the measurements until we got the most possible area. And we had a whole variety of measurements possible. But as it turned out, a square was the shape that gave us the greatest possible area. And the answer to our question actually lies in that investigation. So if a square gives us the greatest possible area, it makes sense that a cube will minimize surface area while also keeping this volume of 16 centimeters cubed. Now remember that surface area is just a sum of all the areas on the sides of a prism. So if I take the area of each of these sides and I add them all together, I'll get surface area. So for us, if we create a cube or a square-based prism, that's going to end up minimizing surface area while maximizing volume. Okay, so in the last example, a square maximized surface area. In this case, it's going to maximize volume. We've added another dimension to the mix, hence the cubed here, and that's what's going to that's how we're going to end up maximizing volume, is by making this thing a cube. So an example here, a popcorn company ships popcorn to movie theaters in large cardboard boxes that have a fixed volume of 500,000 centimeters cubed. It says determine the dimensions of the square-based prism box that will require the least amount of cardboard. So the first question we have to ask ourselves is, what shape will minimize surface area? And based on the discussion we just had, we know that a cube will minimize surface area. So our goal is to come up with some sort of cube with some dimensions that will give us this volume while also minimizing surface area, right? Because that's cardboard, and cardboard costs money. So we know that a cube has a volume of length times width times height. We are given our volume in this case. We know that our volume is 500,000 centimeters cubed, so we can sub that in for volume. And we also know that because we're working with a cube, all three variables, the length, the width, and the height, must be the same. So I can kind of simplify this formula a little bit and just write it as volume equals S cubed. And why don't we just say that S is the length, the width, and the height for our cube. Okay, so we're given the volume, so we can substitute that into our formula, and really all we need to do here is solve for S. S will tell us the length, the width, and the height for our cube. Now this is a pretty straightforward equation to solve because there's only one step. To get rid of this cubed this 3 that's in the power here, all I need to do is take the cubed root. Now that might not be familiar to you, but it's exactly the same as like getting rid of a square. We take the square root. In this case, we take the cubed root, and we write that with a tiny 3 in front of the root sign. So I just kind of place it right inside that little nook there. So that's the cubed root. And when I take the cubed root, I end up getting 79.4 centimeters. So as it turns out, 79.4 centimeters for the length, width, and height will minimize the surface area for this box while still giving us this maximum, this volume that's fixed. Okay, so since we know the length of the measurement of the length, the width, and the height, we should be able to determine how much cardboard we need to build this box. So remember, this is going to be the minimum surface area. So what this question is really asking is, what is the surface area of this cube? So to solve for the surface area, we need to actually come up with a formula for surface area of a cube. Now, we can think about a cube as 6 square faces, right? And you can count them. It's kind of hard to shade on this program, but you can picture like the front face would be 1, this face would be 2, I have a face on the side would be 3, 4, 5 on the top and bottom, and 6 on the back. So I've got 6 square faces. We know the area of a square is length times width. So we have 6 length times widths, but in this case, length equals width. So we're going to call that S. So there's a nice formula for the surface area of a cube. So all we need to do is substitute in our measurement for our length and our width, which we know is 79.4. We're going to square that first and then multiply by 6. Remember, we're going to remember our bed mass here. Brackets and exponents go first. So 79.4 squared, we're going to multiply by 6, and we end up with 38,000 centimeters squared of cardboard. So that's how much cardboard we'll need. That's the surface area to give us this volume, and this will be the minimum surface area. So we'll use the least amount of material possible. All right, so maximizing volume, this is going to be a similar sort of situation. We're being asked to determine the dimensions of a square-based prism with maximum volume, so we want to get the most volume possible, and we're being told that we are using 5,400 centimeters squared of cardboard. Okay, so we know that a cube is going to give us the most volume based on our discussion from earlier in the video, and cubes have 6 square faces. So we know the surface area of a cube is 6 times the length times the width. We just looked at this formula, which ends up being 6 times S squared if we use S for our length and width. Now, what we have to do is take our surface area, put it into our equation, and solve for the dimensions that will give us that surface area. So we're going to sub in 5,400 for surface area. And our goal is to solve for S. So to do that, we're going to divide both sides by 6. And to get rid of the squared, we're going to take the square root, not the cubed root this time, and we'll end up with 30 as our measurement for S. So what does this tell us? Well, we know that a cube's going to have side lengths that measure 30 centimeters. That's going to be the length, the width, the height, everything. So to determine the volume of our cube, we're going to use our formula for volume, which is length times width times height, which simplifies in this case because the length, the width, and the height are all the same. So we're really just multiplying 30 times 30 times 30. That'll give us 27,000 centimeters cubed. Okay, and that should be the most volume possible given the surface area. Okay, great. So another video lesson done. There's no quiz for this one. Really just a couple concepts, mainly that to get the least amount of surface area and the most volume, it's useful for us to use a cube when working with rectangular prisms. That'll give us the most volume while using the least surface area, which again would save money, and that's really what it's all about when you're working for a business. Okay, so next day in class we'll look at some practice problems that apply some of these concepts, and hopefully things will start making sense. Very good. Thanks for watching.